In the third part of Lecture 8, I want to talk to you about linear transformations. So we've seen what a transformation is, we've talked about a matrix transformation, and now I want to introduce another special type of transformation called a linear transformation. And a transformation is linear if it satisfies the following two properties. First of all, it says that if I take any two vectors in Rn, and I first add the vectors and then stick them into my transformation, it's the same thing as first sticking the two vectors into the transformation and adding the resulting vectors. The second property that a linear transformation has is that if I decide to first scale the vector and stick it into my linear transformation, it's the same thing as taking my vector, plugging it into the function, and then scaling the resulting vector. So here I have a transformation from R2 to R2, and I want taking this vector to this vector right here, and I want to show that it's a linear transformation. So I have to show that it satisfies both of these properties. So let's do that. So I take a vector u and I add it to a vector v. So I'm going to first add those two together. So that, of course, means I get the vector u1 plus, clean that up, u1 plus v1 and u2 plus v2. And now I'm going to stick it into my function. So I'm going to get 3 u1 plus v1 plus 2 u2 plus v2 in the first coordinate, or in the first spot. And in the second spot, I'm going to get u1 plus v1 minus 4 u2 plus v2. Okay. Now, what I want to do is kind of get rid of all of these parentheses. I want to re-expand them all. So then I want to put all the u's together and all the v's together. So I can rewrite this as 3u1 plus 2u2 plus 3v1 plus 2v2. And in the second coordinate, I get u1 minus 4u2 plus v1 minus 4v2. Okay, and now using my properties of vector addition, you notice that I can break this vector apart into the sum of two vectors. Right? I can rewrite this as the sum. I'll start a new line here. I can rewrite this as the sum of 3u1 plus 2u2, u1 minus 4u2, plus the vector 3v1 plus 2v2, v1 minus 4v2. And when I stare at both of these vectors right here, I see, well, this is the vector that I would get if I had just plugged u1, u2 into my transformation. So this is the same thing as u1, u2 plus t v1, v2. Okay, so I have the property that I want in the first part is that whether I sum the first vectors together and then stick them in the function, I also get the same thing as first sticking the vectors into the function and then adding the resulting vectors together. Okay, so this again kind of illustrates how you would do a type of proof involving equality. You have two things you want to show equal. You want to show this side is equal to this side, and you have to provide all the justifications in between. So that shows just the first part of being linear. Let's verify the second part of being linear. So if I take t times a constant times my vector u1, u2, so I'm first going to scale my vector. So I get cu1, cu2, and then I put it into my matrix, into my transformation. So this tells me it should be 3cu1 plus 2cu2, cu1 minus 4cu2. Everything inside of this vector has a c, so I can factor it out. So I have c, and then I'm left over with 3u1 plus 2u2 and u1 minus 4u2. And notice that this is what I would get if I had just plugged the vector u1, u2 into my function. So I get the scalar multiple of my original vector u1, u2. Okay, so because this function, here I'll give my hand back here, this function here satisfies both of these conditions, it has to be a linear transformation. Okay, so T is a linear transformation. Okay. So we've learned about matrix transformation and a linear transformation. And this next theorem is very, very important in linear algebra because what it's saying is transformations that are linear transformations are also matrix transformations. And transformations that are matrix transformations are linear transformations. So even though they have two different names, they're actually the same thing. So if somebody says, oh, here's a matrix transformation, you can say, oh, thank you, this is a linear transformation, or vice versa. Here's a linear transformation, here is a matrix transformation. So the above example on the previous page there was a linear transformation as we proved. So the theorem here says that it should also be able to write it as a matrix transformation. And you can do that. You can check, I'll let you do that on your own. You can check that this transformation is the exact same thing as multiplying by the matrix 3, 2, 1, minus 4 by the vector x1, x2. Okay, and this theorem is important because what you're doing is if you're studying matrices, you can really think of it as studying linear transformations. And so at the very beginning of today's lecture, I mentioned that many mathematicians think of linear algebra as the study of linear transformations. And this theorem here kind of explains this connection. Now, the proof is not that hard. We actually have a lot of the pieces available to prove it. You'll notice that it says if and only if, so there's two statements to prove. We need to prove that if we have a matrix transformation, then it's a linear transformation. And if it's a linear transformation, then it's a matrix transformation. So today what we're going to do is we're going to prove one direction, and the other direction will come from tomorrow's lecture, or the next lecture. Tomorrow, I guess, is relatively subjective at this stage. So let's prove that. Here we have a matrix transformation. We're assuming that somebody gives you a matrix transformation, and we want to verify that it's a linear transformation. So we're trying to verify that it has those two properties described in the last definition. So first of all, because it's a matrix transformation, we know that our transformation looks like A times X for some M by N matrix A. Now, in section 1.4, and I can't remember if this is lecture 4 or 5, we showed that multiplying by a matrix by a vector has the following properties. It has the property that if you take a matrix and you take two vectors and you first sum them and then multiply them by A, that's the same thing as taking A times U and adding it to the vector A times V. And we saw something similar for scalar multiplication. Namely, I can first scale the vector by C and then multiply by the matrix A, or I can multiply A by the vector U and then multiply by C. So what we have is that TU plus V is equal to AU plus V, right? Because it's the matrix transformation. But then from using results from section 1.4, we can replace it with this sum, but that's the same thing as TU plus TV. And similarly, TCU is equal to ACU, which is equal to CA times U, which is the same, which is the same thing as c times t times u. Okay, but so thus t is a linear transformation. Okay, so this proved actually one direction of the statement. And for the second statement, we'll come back to that next lecture. Next lecture. In fact, actually what we're going to do is something a little bit stronger, is we're going to do the following, is given a linear transformation, we can explicitly find a matrix A such that Tx is equal to Ax. Okay, so we'll see that in the next lecture. So just to kind of recap the main part of today, this little piece of the lecture is what is a linear transformation, and noticing that linear transformations and matrix transformations are the same. And so I'll take a quick break right there, and this is where we'll start when you come back. Okay, see you in a couple minutes.